In this video we explored the Heaviside step function, and it's going to be key to us for understanding discontinuous forcing functions. That shows up quite a bit. The Heaviside function is defined here, and I'm going to look at its graph in Desmos with you in a minute, but it's defined as a piecewise function which is 0 if you're left less than a certain number, and we're calling that c. So the Heaviside function is this step function we have written down, this piecewise function we're written here, and it's customary to write that as u sub c. Alright, so it's 0 if you're less than c, and it's just constantly 1 if you're bigger than or equal to c. And we can think about that modeling in terms of our harmonic oscillators turning on a switch, possibly for an RLC circuit, or maybe if you're talking about a mass spring system, to adding a constant force to the system. Alright, that constant force might be, say, lifting one side of the table up a certain amount and just leaving it fixed up. Alright, so we're also going to see that a little bit later that we're going to use this to turn on an external force after a certain amount of time. Alright, but let's look at the graph a little bit with this, and I'm going to go over to Desmos for it. I just want to note that this is in the second section in Lumen there about solving Laplace transform with discontinuous forcing functions. Alright, so I've got this plotted here in Desmos. Alright, now I've got the graph of u sub c plotted there in red. Alright, now if I move the slider here, then it's going to change the value of c, which is that subscript. And let's just notice if I move it over to, say, 3, then notice now the function's constantly 0 up to t equals 3, and then it jumps up and is now constantly equal to 1. So we're going to think about turning a switch on after t equals 3. Alright, you're going to go 0 up to 3, and then it'll just be 1 after that. If your switch has constant strength 1, then that's what it would be. Alright, now that's not the only way we're going to use the Heaviside function, but that is its graph. Let's go through a little bit here in Desmos, and then we'll get back to the handout. Alright, so I've got another example listed here, which is sine of t. Alright, now what we're going to see is this combination I have down below here, u sub c of t times f of t minus c. I just want to remind you what happens when we take a function. So I've got sine of t as my function, f of t. And what happens if I subtract the number on the inside? Remember what that does to the graph? It shifts the graph to the right a certain amount. So notice in this picture, the original sine function starts at 0 when, which is the blue graph here, starts at 0 when t is equal 0 and goes up to 1 at pi over 2 and back down to 0 at pi, and so on and so forth. Now if we just look at the red graph, this is shifting the whole sine graph to the right 3 units, so now it's starting at 0 when t is equal 3 and then doing its normal pattern. Now what we've got with this next combination is what happens when you take that and you multiply it by the Heaviside function. Alright, you can kind of see that outline now in green. Alright, now I'll turn the red graph off. So now this is going to be constantly 0 up until t equals 3, and then it starts the function. So it's almost like we're shifting the initial value by multiplying it by the Heaviside function and composing it with t minus 3 in this case. We're shifting the starting value to t equals 3, and then it's 0 up to 3, and then it just starts the function there. I've got a couple other examples, or another example to look at over here in OneNote. Alright, we're going to see that this kind of expression as our external force quite a bit, like in this example. And then we're going to talk about how the Laplace transform comes in. So in this example we've got, I'm calling the function g of t cosine of 2t. But again, suppose we only want to turn on this external force after t equals 3. Alright, so that's going to be our new starting point. Alright, now what we're going to do then is, like we just showed a second ago in Desmos, let's look at this combination where we have the Heaviside function times g of t minus 3. Well, if g is the formula cosine of 2t, that's going to be cosine, and then we're going to replace the t by t minus 3, and we're multiplying in the front by u sub 3 of t. Alright, now I've got this graphed in pictures down below here. In blue, we've got the regular graph of cosine of 2t. Notice it's starting at 0 or 1, pardon me, when t is equal 0. And now the graph in red is just the shift of it. So notice now this point right here, that I'm highlighting in green, that got shifted over 3 units to start at height 1 when t is equal 3. Alright, now the last graph we'll show is what happens when you take this red function, the function I've got whose graph is listed in red there, and multiply it by the Heaviside function. That's going to give us this one here where we're constantly 0 up until t equals 3, and then it starts the ordinary cosine of 2t graph at that point. So again, that's what this combination right here does. So if you want to shift the starting value and just start the function, let it be 0 up until a certain time, that's what the Heaviside function will do. And if you want to start it with that initial value, which is normally the value you get at t equals 0, at that value, and in our case it's t equals 3, then we have to compose the original function by substituting in t minus 3. Okay, so those are the kinds of forcing functions we're going to see in some of our differential equations going forward. Now let's compute their Laplace transforms. Alright, so here is the Laplace transform for the Heaviside function. Alright, now I've put this in using the definition and computing it that way. The first step is just the definition of the Laplace transform. Now, from the first equals to the second equal sign, what are we plugging in? Well, remember what u sub c does. It's constantly 0 up until, if your t values are less than c, and then it's constantly 1 if you're greater than or equal to that value. So really, this is going to be the same as integrating, because it's going to be 0 up to c. We're really integrating from t equals c to infinity, and then when we plug in 1 for u sub c, that's like e to the negative st times 1. Alright, now from there it's just a matter of writing the antiderivative down and evaluating. So the antiderivative of e to the negative st with respect to t is negative 1 over s times e to the negative st. And then we have to evaluate that by plugging in infinity, and I put that in quotes because that's really a limiting process, and then plugging in t equals c. Now, if we're taking the limit as t goes to infinity, this is exponential decay, so that's going to go to 0 as t goes to infinity, provided that this value s is greater than 0. So that way negative s will be negative, and that will be exponential decay. Alright, so if s is positive, then as t goes to infinity, e to the negative st times negative 1 over s will go to 0. Alright, I've actually factored out the negative 1 over x in the next step there. And then we plug in t equals c, and that apparently got left off here. Alright, when I did that, so this should have been negative s times c, and so this should have been 1 over s. After you distribute the negative 1 over s through the parentheses, these two negatives make it positive, and then it'll be e to the negative. Now I just want to switch in the exponent there, the c and the s, so e to the negative c times s. Alright, so it's a pretty simple calculation, and then that shows you what I've got in bold here. The Laplace transform of the Heaviside function, u sub c of t, is e to the negative cs times 1 over s. Now, in terms of the Laplace, the inverse transform, which is the important step for us when we're solving initial value problems, is to invert, to recover the solution in terms of t. Keep in mind here that the Laplace transform of the constant function 1 is 1 over s. So this is related via the Laplace transform to the constant function 1. So what does this really tell us to do? When we see this e to the negative cs, that tells us to multiply the constant function 1, in this case, by u sub c. Alright, so the Laplace transform of that is u sub c. Alright, or the inverse transform of that is u sub c. Alright, next we're going to move on to the composition we were talking about, where we want to say shift a given function to start at a new value like c. Alright, so let's compute that Laplace transform. Alright, so the first step I've done here, I've got some of the work done, and then we're going to finish the rest now. The first step is just using the definition. So it's e to the negative st times the function you're trying to evaluate it at there. Now, in the next step, remember the Heaviside function is 1 or is 0 up until t equals c. So instead of us integrating from 0 to infinity, we're going to be able to integrate from c to infinity, because it's 0. That function is 0 constantly up until t equals c, so there's nothing to integrate. We multiply that by e to the negative st. Alright, now from here we're going to do a u substitution, and now I'm going to write out some of the rest of these steps. So we're going to let u equal what's inside of f, so that's t minus c. The derivative of that with respect to t is just dt. We got to do a couple other things here. One is we're going to have to solve this for t, so t is going to equal u plus c. And the other thing is to change the limits of integration. So if t is equal c, then plugging this into the u substitution, we're going to get u is equal c minus c, which is 0. And if t is equal infinity, that's going to convert over to u equaling infinity also. So the upper limit of integration is going to stay infinity. Alright, so now let's perform the substitution. So we get the integral from u equals 0 to u equals infinity of e to the negative s times u, or t, pardon me, which in that case was u plus c, times f of u, and dt was du. Alright, so we did that u substitution, and this is going to allow us to, after some rewriting, to express this in terms of the Laplace transform of f. Alright, now what we're going to do is split this exponential up into factors. So this is going to be the integral from u equals 0 to infinity, and we can write this as e to the negative s u times e to the negative sc power times f of u du. And then the last thing we're going to do is notice that the only thing that we're integrating with respect to u, so this factor right here can be sucked out of the integral. Okay, and then just notice that u in this case is just a dummy variable, so we could now switch back to t if we want to, and then that right there, if we do so, is really the Laplace transform of little f of t. Alright, so then that gives me the result that I have written down on the next page. What's our conclusion here? We end up with, if we have this combination, the Laplace transform of the Heaviside function u sub c times f of t minus c is e to the negative cs power times the Laplace transform of little f, which I'm writing as capital F. Alright, so capital F here, remember, is the Laplace transform of little f. Okay, now again, the inversion is what's the key part here. So what does this mean in terms of inverse Laplace transforms? So this is the way we want to think about this. Whenever we see this expression, e to the negative cs times the Laplace transform of some function that we know about, then what I have in blue there is the key to this. The negative cs in the front, it tells us to multiply the function f of t, and keep in mind little f, in some other places it's going to be little y, or capital F is related to little f via the Laplace transform. So what does this tell us to do? We need to take this function, little f of t, we need to multiply that by the Heaviside function. Alright, and then we need to evaluate that by replacing t by t minus c. Okay, so that's going to give us, in the end, when we do this inversion, the Heaviside function u sub t of t times f of t minus c. Okay, so that will be a fundamental result. Let's take a look at an example illustrating this. I'm just going to go through one example to finish this video off. Suppose, for instance, that we're looking at this, and this could be a result of solving an initial value problem. We have e to the negative 4s times s over s squared plus 9. Alright, as we've seen in our previous work, we know that this function s over s squared plus 9 is related to cosine of 3t. Okay, now what does the e to the negative 4s tell us in the front to do? This tells us to multiply that function cosine of 3t by u sub, and if it's negative 4s, then that's playing the role of c up here. So we're going to multiply by u sub 4 of t, and then we're going to go over here and we're going to evaluate this at t minus 4. Alright, so we convert this over. What is this related to via the Laplace transform, or if you want to say it this way, via its inverse transform? We're going to get u sub 4 of t times cosine of 3t and the cosine part is going to be evaluated at t minus 4. So really what we're getting here is u sub 4 of t times cosine of 3 times replacing t by t minus 4. So times t minus 4.